Chapter 8, Section 3, this is the video 77. The title is Trigonometric Integrals. So there's lots of different ways that we're going to handle trig integrals because simple, straightforward u substitution doesn't work too well. The problem with u substitution is if I have sine squared and I let u equal sine, then du is cosine, and there is no cosine in the original question. So trig needs to be handled a little bit differently. We're going to need to rely on some of our pre-calculus things. So here are your Pythagorean identities from pre-calc, and most important is probably this middle one, tangent squared plus 1 is secant squared. Since all these have even exponents, realize that you can convert even powered trig functions into something else. So if you need to get rid of sine squared, you can turn it into 1 minus cosine squared, etc. Okay? Another thing that's going to be very helpful towards the end is sine or cosine degree even double angle identities. If I have a sine squared or a cosine squared, I can turn it into something with cosine to the first. Okay, the argument doubles, and that's okay. We can just do a u substitution. But by using these double angle identities, sine squared, the problematic squared value, becomes to the first, and we can handle that a little bit easier. Here's a proof if you're interested, but you are not going to have to create the proof. It's okay if you just memorize these identities there. So case 1 here and case 2 are both going to be handled on the same screen. This is when sine and or cosine are odd values, okay? Method 1 says you're going to save one and convert it into the other. So what does that mean? If I see sine to an odd power, I'm going to pull one sine out, and that's going to be part of my du, and then I've got sine to the fourth. Now I'm going to convert the even powered part into the other trig function, cosine. So sine to the fourth is the same thing as sine squared squared. Sine squared is 1 minus cosine squared. So I've got this, and now when I expand this out, I have this. And the reason why I save that sine x dx is now I can go through and let all of these be a u, let u equal cosine x, and then I've got du of sine x ready to go. So I'm going to take these three terms and I'm going to distribute sine x to all three of these. The antiderivative of sine x is pretty straightforward. That's just negative cosine x. Bringing out the negative 2, I have cosine squared times sine x, let u equal cosine x. Therefore, du is negative sine x dx, and I'm going to use the same u substitution on this one here. U is going to be cosine x, so this is u to the fourth, and du is negative sine x dx. So both of these are going to have sign changes. This negative is going to come outside, and this negative is going to come outside, but I've got antiderivative u squared du and antiderivative u to the fourth du, which we can do pretty quickly. 1/3 cosine cubed, 1/5 cosine to the fifth. Replace your u back with cosine, and you're done. Don't forget the plus c at the end. So the idea is odd powers separate, have one odd, one even. Have one to the first and then a remaining even, and then use the even to convert to the other trig function. So a second example of that is happening here. I've got cosine cubed and sine to the fourth. So since cosine cubed is odd, I'm going to separate that one and say cosine to the first, cosine squared. This to the first power is going to stay. Cosine squared is going to get converted into sine squared. And now I have cosine times these two things here. So cosine times sine to the fourth and cosine times sine to the sixth. Bringing the sine to the fourth produces sine to the fourth and sine to the sixth. Again, both of these are done with u substitutions. U is going to be sine x, so I've got the antiderivative of u to the fourth. Du is cosine x, so that's taken care of there, and you wind up with that statement there. Okay, so for cases 3 and 4, we're going to be working with tangent and secant, and these are a little bit more challenging because they're not straight back and forth derivatives like sine and cosine. The derivative of secant is secant tangent, and the derivative of tangent is secant squared. So if I see this, and if I know that I would like to have a secant and tangent, I'm going to pull a tangent out and a secant out and leave that as my du. That leaves behind even powers of tangent and secant. So pulling a tangent out leaves a tangent squared behind. Pulling a secant out leaves a secant to the fourth behind. Since they're even powers, it's now easy to convert using the Pythagorean identities between tangent and secant. I'm going to convert this tangent squared into secants because the derivative of secant is sitting right there. So tangent squared becomes secant squared minus 1 from the Pythagorean identities. Distributing my secant to the fourth, I've got this. And then now I'm going to let u equal secant. Du is secant tangent, so I've got the du right here, and I've got u to the sixth and u to the fourth. So separating u to the sixth, u to the fourth antiderivatives are pretty straightforward. You just get 1/7 secant to the seventh and 1/5 secant to the fifth, and don't forget your plus c. So I'm going to refer you to the book, for example, 5 on page 540, because this secant even is pretty much the same process. If you have secant to a high even power, pull out one secant squared, and then the remaining even secants will be turned into tangent statements. That way you can let u equal tangent, du is going to be secant squared. That's what you pulled out and saved before you started the process. One thing I want you to realize is that please don't go running to sine and cosine immediately. Some people don't like working with secants and tangents, so they turn them into sine and cosine. And if you can just get a couple of these derivatives memorized, then the secant method and the tangent method is a little bit more efficient than turning everything into sines and cosines. So the most challenging ones actually look like they'd be the easiest. If I want the antiderivative of sine to the fourth, you'd think that would be pretty straightforward. But what we have to do is convert sine to the fourth, this even sign, into an odd power. And you're going to be using the identities that showed up on the first page. So cosine squared is 1 plus cosine 2x over 2, and sine squared is 1 minus cosine 2x over 2. So if I can get sine to the fourth into sine squared, I'm going to take sine squared and replace it with this. And again, the advantage is that I no longer have an even power for cosine, it's to the first. So when I multiply that out, first thing I'm going to do is I'm going to take the denominator of 2 square and put it out front to lose that fraction. So 1/4 comes out front. 1 minus cosine 2x squared is 1 minus 2 cosine 2x's and plus cosine squared 2x. So 2 of these 3 are pretty straightforward. The antiderivative of 1/4 dx is just 1/4 x. 1/4 times 2 is a half. The antiderivative of cosine 2x is just going to be an old u substitution. The power for cosine is 1, and we know how to deal with that. We're going to have to do a u substitution on the argument, but that's not too bad. The bad news is that we still have another even power right here, so we're going to have to use this formula over here again. So I've got 1/4 antiderivative of cosine 2x dx. I'm going to use this again, but notice that because the argument is 2x, now inside the squared becomes to the first power, but the argument becomes a 4x. Now I've gotten rid of all the squares. I just need to again simplify this step here. 1/8 antiderivative of 1 is 1/8 x. And if I do a u substitution, 1/8 times 1/4 for the argument is 1/32. Antiderivative of cosine is sine. So your final answer is all this plus c.